All right, IBAISL2. Today we're starting our final learning target of the semester, which is periodic functions, or as I call them, sinusoidal functions. Not just me. A lot of mathematicians call them that because they are that. The two main ones we're going to be working with today are the sine of x and the cosine of x. It's not always equal to f of x and g of x. It can be different letters, but just in general, if you see a sine of x or a cosine of x, those are sinusoidal functions. Sinusoidal is in my top 5 favorite math words. I think it's the OI combination that makes it so fun to say. Sinusoidal. So we're going to do one problem today with a couple different parts that all have to do with a Ferris wheel. Ferris wheels are the classic sinusoid problems because they're kind of like the unit circle. Now, we're not going to go over the unit circle in detail. I'm really just going to show you a little bit about this Ferris wheel problem, and then we'll turn it into a sinusoidal function. So, key facts. The Ferris wheel has a 70-meter radius. Theta, and that's how you say this right here. This is theta. Theta represents the angle measured anti-clockwise. Now, when I say angle, this is going to be in degrees. I realize in other classes that you may have done radians, but we do not do radians in this class. We keep it all in degrees. So make sure your calculator is in degree mode from here on out. So that angle is going to be measured anti-clockwise. Love that British term, anti-clockwise, from the x-axis. Find all the angles for when pod P is, and then we're going to do 40 meters above the x-axis. Well, first up, with all these problems, we got to start with a picture. So, if we want to figure out when it's 40 meters above the x-axis, let's draw our axes on here. So, pod P is going to start here on the x-axis. Remember, this is your x and this is your y. Then it's going to rotate anti-clockwise, so going this direction around the circle, counterclockwise. We want to know when it's 40 meters off the ground. So if you picture your pod P traveling around this circle like this, first, if the radius is 70, like if this is 70 meters from, here to here, it's going to be 70 when it hits up at the top. So that's the tallest that the pod is going to get off the ground is going to be 70 meters because that's the radius. So somewhere in between 0 and 70 is going to be a 40. So it'll probably happen somewhere around here. It's not necessarily halfway or anything like that. We don't really know how far it is, but there will be a point where this is 40 and then this radius is 70. The theta that we are looking for is connected to the x-axis. It's right here. This is the theta. Now, we need to find that theta for when it has a height of 40 off the x-axis, but that is not the only place where this happens. There's going to be another spot. If you picture taking this triangle right here, or this quadrant, and then flipping it over into this quadrant. Whoops. There's going to be a matching one on this side. So somewhere over here, there will be another spot where it hits 40 again, where this is 70, this is 40. But then the theta is not going to be right here. The theta will be all the way from the x-axis over to here. So there's actually 2 different spots where this hits a height of 40 meters off the x-axis. If you were to do a little SOHCAHTOA on this triangle right here, 40 is the opposite side and 70 is the hypotenuse, which means we could set this up and say sine of theta equals 40 over 70, or we could reduce that to sine of theta is 4 over 7. Now, we could do an inverse sine on our calculator right now and get the inverse sine of 4 over 7, but it's not going to tell us this second spot over here of when it hits 40 again, because your calculator just searches for one answer, and once it's found one, it's done. It doesn't care anymore. So I'm going to show you guys a method of graphing this as 2 separate functions. And when I say this, we're going to graph this side right here as y1 And then we're going to graph this side, terrible curly bracket, as y2. Now, before we get into this, I'm going to scroll down to show you all the steps that you're going to take to be able to do this. So this is like, in general, the cheater way to solve an algebra equation is that you graph both sides of it and then you find their intersection. So these steps work on a TI-8483 variant calculator. You're first going to hit your y equals button in the top left corner, and then you're going to punch one side of the function into y1 and the other side into y2. You are then going to hit your window button and adjust your window so you can see both of the functions and the intersection that you want to find. Might be multiple intersections, like in this problem I'm doing now. Then you're going to hit your graph button, make sure you can see everything, and then hit second trace, which is the calc button, and find the intersect function. Once you have intersect, it's going to pop you back to the graph menu, and then there's going to be a little blinking cursor on one of the curves or lines that you graphed. And it's going to say highlight, it's going to say first curve. So highlight the first curve and then hit enter. Then your marker should jump to a different curve or line, and then it's going to say second curve. So you find, make sure you're on the other one that you want, and then hit enter again. Then it's going to do a funny thing where it asks you to guess. The guess is really just if there's multiple intersections on the screen, you can tell it which one to zero in on. You do not have to get it right on the money with the guess. You can just get it sort of close and, just in the neighborhood and hit enter a final time. When you do that, you're going to get an x equals and a y equals at the bottom of your screen, and the x equals is your answer. So, if I punch sine of theta into y1, then with your window, you're going to need to design a window that makes sense to view this. So we're going to say that x min is 0, because remember the x's are the thetas, and that's your degrees around the circle. So then your x max is going to be a full circle, which is 360. In terms of your y min and your y maxes, okay. It just needs to be big enough to cover this, like to see this 4/7. So 4/7 is like 0.5 on a calculator, around, or 0.6. So let's go up to like maybe 1.5 and down to negative 1.5. So do negative 1.5 on the y min, and then the y max, we'll do positive 1.5. Then when, this, sorry, I keep saying this, like you guys can see what I'm talking about. This is in your y1 and this is in your y2. Go ahead and hit enter, and you should see something like this. You'll see a really nice sine curve. So the sine curve basic features are it starts with a mountain, then it comes back to sea level, and then it goes into the valley and then back up. We'll talk more about like the parent functions of sine curves next class. Then you should see the second line. So the second line is 4/7. That's just a horizontal line that cuts through about 0.6. So it'll go through and touch two places on your curve. Now, that line is not straight. That means that this intersection and this intersection are the answers to this problem. So, when you do your intersect function and do all the steps that I ran you through, you should get that x is 34.8 on this first one. And then do it again for the second one. The second one is 145, about three significant figures. So these are the degree answers to this problem. It's telling us that like in this circle, you're going to rotate 34.8 in this first little rotation here, and then you're going to rotate 145 for the second one. So the second one starts here and goes 145 all the way to this spot. So those are your answers. 34.8 degrees and 145 degrees is when the pod will be 40 meters off the ground. So far, so good. Second part, the last part of this question, we're going to have to find when the pod is 20 meters horizontally from the y-axis. So first, let's draw a picture of this. No, please. So 20 meters from the y-axis, there's actually like 4 different spots where this happens, because if you picture, this being the y-axis, as the pod goes around the circle this way, there's going to be a spot right here where you can draw a triangle where this distance right here is 20 meters. So if I zoom in here, there's a spot where this is 20, and this makes a right triangle. But then if you flip that into the second quadrant, the quadrants. This is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. If you flip it into the second quadrant, you'll get another spot where it's also 20 meters away from the triangle. So there's going to be an identical one where it's at 20 meters again, where this distance is 20 meters from the x-axis, or from the y-axis. And then if you flip it into the third quadrant, we'll get another spot right here. Gosh, why is that bothering me so much? Just freehand. There we go. There's another spot where it's 20 meters, but then there's another one in the fourth quadrant as well. So in between 0 and 360, like that's what's happening with this. The domain of this problem is that theta is going to be in between 0 and 360. There's actually 4 different spots where that happens. I realize in terms of the Ferris wheel problem that on this side over here, that these are, it's still 20 meters away, because you can't really have negative distance in the real world. But technically, mathematically, this 20 on this side is going to be a negative 20. So I think in terms of the problem, we're actually not going to find this quadrant or this quadrant, because those are like negative 20 meters. If you were to do a little SOHCAHTOA on this triangle right here, we know that the hypotenuse is 70, because it's a 70-meter Ferris wheel. And then we know the 20, this side. So we have adjacent over hypotenuse, which is the cosine. So we're trying to figure out cosine of theta is equal to 20 over 70. Or, if we reduce that, 2 over 7. So we're going to take the same strategy as we did before, where we're going to graph both sides. This is going to get punched into your y1. This is going to get punched into your y2. Now, your window setting from the first part of the problem should be fine, so don't change it. So we're just going to graph those into y1 and y2. When you do that, you will get a nice cosine curve. Once again, probably next video, we'll talk more about what an average cosine looks like. But you get something like this on your screen. It starts at the top of the mountain. Oops, stop it. And then it dips into the valley, it dips back to sea level, and then it goes into the valley, and then it comes back up, and then it goes all the way back up again. This is your sort of parent curve of a cosine, and we'll talk about it more next class. Then the 2/7 that you graph should cut a line through the graph right about here. That means that the x value here is one of your answers and the x value here is one of your answers. When you do your intersect function, you should get that this one is 73.4 degrees, and this one is 287 degrees. 3 sig figs. So that makes sense, the 287, because as you go around the circle, this is 0 degrees here on the x-axis, and then up top, this is 90 degrees, then this is 180 degrees over here, then 270, and then a full 360 back. So, what is it, 287? That would make sense that this is 287 because it's this spot right here is in between 270 and 360, and it's a little closer to 270 than 360. So it would make sense that if you start here and then rotate all the way around to here, that you get, what, 287 degrees. So at 73.4 degrees and 287 degrees, the pod will be positive 20 meters away from y-axis. Okay, you guys, that's it for today. Next class, we'll get more into like how to graph these by hand, and we'll talk about some parent curves and some transformations and stuff, but day one was just a word problem.